Welcome back to the deep dive. We are so glad you're here because today we are tackling what is, well, arguably the holy grail of modern tech. We are talking about AGI, artificial general
The
intelligence.
big one. The theoretical moment the machine becomes as capable as a human, or, maybe even more so.
Exactly. And if you follow the news or even just look at your social media feed, you know the main story. It's this bigger is better theory.
Right.
We have these huge, large language models, GPT-4, Gemini, Claude, and the assumption is just, well, if we keep feeding them more data, buy more GPUs, make the networks denser, eventually something magic happens.
A threshold is crossed.
Yeah, AGI just sort of appears.
That's the scaling hypothesis in a
Yeah.
nutshell. And it's the engine driving, literally trillions of dollars in spending right now.
Mm.
The whole idea is that quantity eventually just becomes quality.
But today we are unpacking a research paper that basically yells stop. It suggests we might be driving, extremely fast down a dead-end road. The paper's called Rethinking AGI, Emergence Through Multi-Agent Systems and Statistical Mechanics by Gaurav Chopra from Purdue University.
And it is a heavy hitter. It pulls from computer science, neuroscience, and maybe surprisingly thermodynamics to argue that a single giant model it will never be AGI.
Never. That feels like a bold claim. I mean, these models are getting so smart they can pass the bar exam.
They can. But Chopra's point is that intelligence isn't about having one giant super smart brain. It's about interaction. It's an emergent property.
Okay.
So the mission for this deep dive is to figure out why the future of AI might look less like some godlike oracle and more like a swarm of bees. Or maybe corporate boardroom.
I like that image, a boardroom. Okay, so let's start with the status quo to really get the critique. The paper calls our current best models monoliths. What makes them monolithic, and why is that such a bad word here?
Well, think of a monolith literally. It's a single solid block of stone. And when you look at something like GPT-4, for all its brilliance, it is a single static thing.
A single artifact.
Exactly. The paper calls them statistical mirrors. They reflect the data they were trained on, but they don't actually inhabit the world.
Reflecting versus inhabiting. Wow, that feels like a really crucial distinction.
It's the whole ballgame. Chopra lists four specific failures of these monolithic models that stop them from being AGI. And these aren't just little bugs, like getting a math problem wrong.
These are structural failures.
Yes. The first one is adaptivity.
Okay, but wait, let me push back on that a little. I can tell a chatbot, hey, change your tone, be more professional, or write that code in Python, not C++ Air, and it adapts. Isn't that adaptivity?
That is, well, it's stylistic mimicry. It's working within the bounds of what it's already been trained on. True adaptivity is about pivoting when the actual goal changes or the environment shifts in a way you've never seen before.
Huh.
A monolith, when it hits a scenario that's way outside its training data, it doesn't. It doesn't restructure its own approach. It just waits for you to prompt it again. It has no internal drive to succeed that forces it to change strategy on its own.
Got it. So it's reactive, not proactive. It's always waiting for the user to be the driver.
Precisely. Which brings us to the second big flaw, context awareness.
Yeah.
Or, just memory and a sense of time.
Right. This is the 51st dates problem that we're always joking about.
It is. Every single time you open a new chat, the model is a blank slate. It has no biography, no long-term memory of past decisions, unless you cram it into the context window. A human grows and learns over time. A model just resets. It's static.
It has no sense of next week.
No. And without a sense of time, you really can't have the fourth point the paper makes, which is long-term planning.
Right.
You can ask an LLM, write me a marketing plan, and it will spit out text that looks like a plan. It understands the grammar, the syntax of planning, but it isn't actually executing that plan, checking results against reality, adjusting, and remembering what worked.
It's just predicting the next word in the sentence about a plan.
You've got it. It's simulating the output of a planner, not actually doing the planning. It's a subtle difference, but it's massive.
Okay, what's the last one?
The final flaw is maybe the most dangerous from an engineering standpoint: vulnerability. Because a monolith is one giant interconnected block, it has a single point of failure.
Yeah, we see this with jailbreaks or adversarial inputs. You find one weird turn of phrase and the whole thing can fall apart or start spewing nonsense.
Exactly. If one tiny part of the network gets confused, that error can just cascade through the whole system. There's no backup, no internal check saying, hey, that part of the brain is acting weird, let's ignore it. The monolith stands or falls as one piece.
So, okay, if the monolith is a dead end, we need a new way to define AGI. The paper doesn't just say make it smarter. It gives a really functional definition that seems harder to game.
It does. And this is key if you want to cut through the marketing hype. Don't look at benchmark scores on some standardized test. Chopra says true AGI needs a system that can do 4 things at once: adapt to changing goals, maintain a memory, resolve internal conflicts, and plan over long time horizons.
And the argument is that no single algorithm, no matter how big, can do all 4 of those things well at the same time.
Correct. It's a classic trade-off problem. An architecture that's built to be a perfect, rigid memory bank might be awful at creative adaptation. So instead of trying to build one super brain,
You break it down.
you break it down. We need agents.
Let's define that term really carefully, because agent is another one of those buzzwords that gets thrown around all over Silicon Valley. How does this paper define it?
The definition here is very strict. An agent has to be autonomous. It needs to maintain its own internal state. It knows, how am I doing right now? But here's the real kicker. It has to make decisions based on local observations.
Local, meaning the agent doesn't know everything that's going on.
Exactly, and that is a feature, not a bug. In a monolithic model, the system tries to achieve this kind of global omniscience. It tries to hold the entire internet in its head at once.
Which is impossible.
It's computationally exhausting, and it's why they hallucinate, because you can't know everything perfectly.
It's like trying to memorize the entire Library of Congress yourself versus having a team of researchers where one has the history book, one has the science book.
That's a perfect analogy. In a multi-agent system, or MAS, which is what the paper proposes, you have these specialized agents. Each one has partial knowledge. And this brings us to the core physics concept in the paper. This is the real aha moment.
The temperature analogy. I loved this part because it takes something we all understand and just flips it on its head.
It completely reframes the debate. Ask yourself, what is temperature? If you take a single molecule of air in a box, does that molecule have a temperature?
No. I mean, it has a velocity, it has energy, but hot or cold for just one particle, that doesn't make any sense.
Right. Temperature is a statistical property.
Yeah.
It only exists, it only emerges when you have a massive crowd of molecules all bouncing off each other. The heat is just a description of their collective chaos.
And Chopra is saying intelligence is the same thing?
Yes. That's the heart of the argument. We're trying to build a single smart molecule by making GPT-5 bigger and bigger. But intelligence might actually be the heat that emerges when you get a whole swarm of simpler agents interacting in a really complex way.
So AGI isn't a thing you build. It's a phenomenon that happens when the system gets complex enough.
That is the shift. It moves AGI from an engineering problem, like building a bigger water tank, to a physics problem, like managing the interaction of atoms to create steam.
Which leads us straight into biology, because if we look at the only example of general intelligence we actually have,
The human brain.
it totally supports this swarm theory, doesn't it?
Completely. You know, we had this sort of egocentric view that I am a single thing. I have one brain, one thought process. But biologically, your brain is a multi-agent system.
Right, we're not just one big neuron.
No, we're billions of them. But more than that, cognition happens in neuronal assemblies, groups of neurons that specialize. You have regions for vision, for language, for fear. They're all distinct modules that have to talk to each other.
And they don't always agree. I can feel scared while at the same time knowing I'm perfectly safe.
They almost never agree. But there's a specific mechanism the paper highlights that really drove this home for me. It's the brain's immune system.
The microglia. I have to admit, I had never heard of these in the context of AI before.
It's incredible. Microglia are these little cells that basically patrol your brain. Their job is to find synapses or neurons that are dysfunctional or hyperactive or just noisy. And when they find them, they prune them.
They eat them.
They literally eat the bad connections, save the whole network's efficiency. It's real-time hardware editing.
Ruthless.
It is. Now compare that to GPT-4. If a part of that model starts to hallucinate and generate false information, there is no internal microglia to go in and eat that error. The error just stays. It gets amplified.
Because the monolith is a rigid block. It can't prune itself without an engineer stepping in and retraining the whole thing, which takes months and millions of dollars.
Exactly. But in a multi-agent system, if you have a fact-checker agent and a creative writer agent, and the writer starts making up fake dates,
The fact checker can flag it.
right, the system can basically vote to ignore the writer agent. It has redundancy. It's robust.
That makes the system so much more resilient. If one agent fails, the swarm just corrects and keeps going. It's like the difference between a glass vase shattering and a cut on your skin healing itself.
That's the biological resilience we're missing in AI. And the paper argues we can only get there by moving to this decentralized, multi-agent approach.
Okay, I want to get into the how of this. The paper talks about statistical mechanics. Now, we promised we wouldn't ground you in math, but we have to touch on entropy because it's so central.
We do. And it's not as scary as it sounds.
Yeah.
So in physics, and in this paper, they look at something called a Hamiltonian cost function.
Which is just like an energy budget. Right.
Yeah, think of it as a measure of unhappiness in the system. Nature wants to minimize energy. But for intelligence, you have to balance two opposite forces, order and disorder.
Order makes sense. You want the AI to be accurate, consistent.
Right. That's a low temperature state, rigid, predictable. But if your AI is 100% ordered, it's just a rock. It does the same thing every time. It can't learn, it can't adapt.
But if it's too disordered,
it's high temperature. It's total chaos. Random noise. True intelligence lives on the edge of chaos. The paper talks about managing Shannon entropy.
a measure of information or surprise.
Exactly. Imagine a swarm of agents. As you add more agents, the number of ways they can interact just explodes exponentially. 2 agents can talk one way, 10 agents can talk in millions of ways. That's an explosion of entropy of possibility.
Which sounds like a total nightmare to manage. How do you stop that from just becoming noise?
Well, that is the definition of intelligence, according to this source. Intelligence is the ability to navigate that giant space of possibilities efficiently. You want this system to explore enough to be creative, that's the high entropy part, but also converge on a useful answer that minimizes surprise. That's the low entropy part.
So you need enough chaos to find a new solution, but enough order to actually solve the problem.
Exactly. And this leads to the paper's wild prediction about how AGI will actually show up. It won't be a gradual slope where the model gets 1% smarter every day. It'll be a critical point, a phase transition.
Like water turning to steam.
Precisely. You heat water, it gets hotter and hotter.
Right.
Still water. Then, at 100 degrees Celsius, boom, a complete state change. It becomes steam. Chopra suggests that once we get the architecture of these agent swarms right, we will hit a critical point where collective intelligence just suddenly emerges.
That is both a thrilling and a slightly terrifying thought. Phase transitions are sudden. You might not see it coming.
They are nonlinear. They change the game overnight.
Let's bring this back to something concrete. We talked about conflict. The paper argues conflict resolution is a superpower of these swarms. Why would we want our AI to fight with itself? That sounds completely counterintuitive.
Because that's how truth is found. Think about our legal system. You have a prosecutor and you have a defense attorney. They have opposite goals. They are supposed to fight.
And the truth, or at least the verdict, emerges from that friction.
It does. A single monolithic model is like a judge who is also the prosecutor and the defense. It's playing all the roles in its head, so there's no real tension. It just simulates an argument.
It creates an average, a bland compromise that might even be a hallucination.
Right. But in a multi-agent system, you can literally program one agent to prioritize safety, and another to prioritize efficiency, and a third to prioritize cost. Then you give them a task, and they have to negotiate.
We can't use that fast route. It's not safe.
But the safe route is way too expensive.
Exactly.
That negotiation is what mimics real human reasoning. The paper mentions the tragedy of the commons, the classic problem where individuals ruin a shared resource. Research shows single agents just get greedy and fail. But a system of agents, with communication and rules, they can solve it. They can coordinate.
That implies AGI isn't just about raw intellect. It needs a social structure.
It implies that intelligence is a social structure. You can't have high-level reasoning without the friction of different perspectives.
So if we buy into this, that the future is swarms, not monoliths, what does the architecture look like? What's the path forward?
The paper lays out a blueprint. It involves 3 main pillars. First, ensembles of agents with heterogeneous roles.
Heterogeneous.
Right.
So different. Not just 10 clones of ChatGPT talking to each other.
Definitely not. You need specialists. A coder, a critic, a historian, a user proxy. Diversity is key.
Okay, what's second?
Shared memory modules. The agents need a central whiteboard where they can all write down and read the current state of the world. This solves that 51st dates problem. They are all referencing a shared, persistent reality.
And the third piece?
Environment coupling. The system can't be a brain in a jar. It has to act, get feedback from the real world, and update its memory. It needs to feel the consequences of its decisions to actually learn.
And if we build this, how do we know it's working? The paper says we should just throw out our current benchmark.
Forget the bar exam, forget the SATs. Those tests are for static knowledge. The real metric for this kind of system is adaptive success. Can the swarm run a scientific lab? Can it manage a city's power grid during a hurricane? Can it negotiate a peace treaty?
Wow. So it's a shift from can it write a poem to can it survive and solve real problems in the wild?
It changes the entire goal from scale to structure. We have to stop obsessing over the size of the model, the number of parameters, and start obsessing over the topology. How do the agents talk? Who gets a vote? How is conflict resolved?
You know, as we talk through all this, I find myself feeling strangely relieved.
Relieved. How
Yeah.
so?
Well, the monolith idea, this super intelligent God AI that knows everything, it's so alien, it's cold, it feels uncontrollable, but a swarm, a team of specialists arguing, voting, fixing each other's mistakes, that sounds like a company. That sounds, well, human.
It aligns AI development with everything we already know about biology and physics and sociology. Nature didn't build one single giant organism to solve evolution. It built ecosystems. It built ant colonies. It built societies. This paper is basically saying, take the hint.
Take the hint. Nature already solved general intelligence. We just need to copy the architecture.
And it suggests the winner of the AI race might not be the company with the biggest data center, but the one that figures out the best way for small, specialized models to collaborate.
That kind of democratizes things, doesn't it? You don't need $1 trillion if you have the best swarm architecture.
In theory, yes. It shifts the value from raw power to sophisticated design.
So for you, listening and trying to make sense of all the AI headlines, when you see a new model release that boasts about having 10 trillion parameters, maybe look a little closer. Ask yourself, is it just a bigger block of stone? Or is it a team?
The future is almost certainly distributed. It's messy, it's argumentative, and it's collective.
I want to leave you with one last thought to chew on, something that really stuck with me from Chopra's paper. He defines AGI as qualitatively intelligent collective behavior.
It's a really profound reframing.
It is. It forces us to ask, have we been looking for intelligence in the wrong place this whole time? We keep asking, how smart is this machine? But maybe the real AGI question is, how well does the system listen? How well does it negotiate? How well does it work together?
If nature is our guide, intelligence isn't something you have, it's something you do together.
A brilliant place to leave it. Thank you for helping us untangle the swarm today.
My pleasure. Always great to be here.
And thank you for listening. We'll see you on the next deep dive. Keep looking for the patterns in the noise.